right, this question is the quiz for pre-ACE physics from this date, May 14th, 2021. And the question reads, a progressive wave y passes a point P, the variation with time t of the displacement x for the wave at P is shown in figure 5.1. So they give us a displacement in millimeters, and it looks like the maximum displacement up here is 4 millimeters, right? That's the amplitude of the wave. And it goes to -4 millimeters at the trough. We're plotting time on the x-axis, and it looks like there's an entire wave form here where it's crossing at 0.4 seconds. So right away, I kind of like to put that down. The time period of this wave is 0.4 seconds. We can just read that off of the graph. Also, we can read that the amplitude is 4 millimeters. Okay, so maybe we'll need that. It says the wave has a wavelength of 8 centimeters. Note that all we know about is the time on this axis. So they tell us the wavelength. Okay, the wavelength is 8 centimeters. So we got all that. Determine the speed of the wave. So the velocity of a wave is going to be distance divided by time, like it is with anything. And we've got the time and we've got the distance, right? The wavelength of the wave is its distance. Yeah. And it takes this much time for that distance to propagate. So we've got 8 times 10 to the -2 meters, right? 8 centimeters divided by 0.4 seconds. We got 8 times 10 to the -2 or 0.08 divided by 0.4, 0.2 meters per second. Sometimes students will right away calculate the frequency, say, oh, well, that's 1 over t. And so if we did 1 divided by 0.4, we've got the frequency of 2.5 hertz or 2.5 reciprocal seconds. And then another form of the sort of velocity of a wave, because 1 over t is f, we could write it like lambda f. And so 2.5 times 8 centimeters is another way to sort of think about calculating this velocity. So they're both identical ways to solve it. So 0.2 or 0.20 meters per second. It says a second wave z has wavelength 8 centimeters and amplitude 2 millimeters at point P. Waves y and z have the same speed. So they have the same wavelength, they have the same speed. We could calculate, it would have the same frequency. For the waves at point P, calculate the ratio of the intensity of wave z over the intensity of wave y. So it's the ratio of the intensity of z to the intensity of y. Now remember, we knew what the amplitude of wave y was. It had an amplitude of 4 millimeters. This one is saying that we've got an amplitude of 2 millimeters. So the amplitude of y was this, the amplitude of z is only 2 millimeters. Now intensity is proportional to amplitude squared. So if we want to look at a ratio of intensities, we have to look at a ratio of these amplitudes squared. And so it would just kind of go like, the intensity of z is going to be proportional to its amplitude squared. So intensity of y proportional to the amplitude of y squared. So we can just kind of consider this. So we got the amplitude of z squared over the amplitude of y squared. 2 squared is 4, 4 squared is 16. So we would get a fourth, or 0.25 should be the ratio of those intensities. And that's worth 3 marks right there for 0.25. All right, now question 6 was not part of the actual quiz, but it is something that we're gonna work through as a preview sort of for next week. All right, so tally up your marks on what we've done so far. 5 total marks, 3 for that ratio, 2 for the speed. All right, so it's out of 5 for the quiz. All right. But I would expect that you've got the additional working for this question as well. So question 6 says, describe the conditions required for 2 waves to be able to form a stationary wave. So remember, we talked about this very briefly yesterday. We said if an outgoing wave goes out and then it's reflected by some barrier, it's going to come back and interfere with itself. And so the wave is going to be coherent. The two waves are coherent. The outgoing wave and the reflected wave are coherent. That's necessary to have interference. Okay, so the waves must meet, okay, and so they have to sort of overlap, right? The waves must meet and be coherent. The waves travel, so it's a progressive wave that transfers energy. The return wave comes back, and now it's a stationary wave that is no longer transferring energy, right? So it's like two progressive waves that are traveling in opposite directions interfere and can make a standing wave. The waves travel, let's say, the two progressive waves travel in opposite directions. Meet and interfere. Because it's the same wave, we can ensure that their frequency is the same and remains the same, and therefore they are coherent. So that's a necessary condition, and they had actually meeting, so they have to actually cross through each other and have that interference. A stationary wave on a string has nodes and antinodes. The distance between a node and an adjacent antinode is 6 centimeters. State what is meant by a node. So it is no displacement. It's an area on the stationary wave that is no displacement. So these points right here where the waves have sort of canceled each other out, these would be the antinodes. So it's telling us that we have sort of like this series of loops is one way to think about a stationary wave. And the antinodes are here and the nodes are here. So they're telling us it's 6 centimeters to get sort of from there to there. An area of no displacement on a stationary wave. We saw this word node with electricity. We said Kirchhoff's first law, all the charges going into a node come out of it. So it's also like a junction in a circuit. But in this case, it's sort of this point right here, it's area of no displacement. Calculate the wavelength of the two waves forming the stationary wave. So if they tell us that there's 6 centimeters from antinode to the adjacent node, how much of a wave is that? Well, that's a quarter of a wave, right? That would be half a wave. So we have to go all the way sort of up here. So you just have to say from an antinode to an adjacent node, that's only 1/4 of a wave. So a quarter of a wave is 6 centimeters. If I multiplied both sides by 4, I'd realize the wavelength is 24 centimeters, or 24 by 10 to the negative 2 meters. They want it in centimeters, so you just leave it like that, 24 centimeters. State the phase difference between the particles at 2 adjacent antinodes of the stationary wave. So the phase difference between 2 adjacent antinodes. So if we look at this figure up here, here's an antinode, here's the adjacent antinode. And remember what we said about all the particles that occupy sort of adjacent loops. So you're looking at sort of the stationary wave at sort of one instant in time, and at the next instant, the wave is going to look like this. So all of these particles, are moving up because they're going to occupy this position a moment later. All of these particles here are all together moving down because they're going to occupy this position. And so you sort of see like, you're seeing 2 instances of time when you're looking at the loops in a stationary wave. You're sort of visualizing both the outgoing and the return wave interfering. But sometimes you'll see it sort of drawn like this to remind us that, oh yeah, those string particles, let's say, it is a string in this example, they only can exist in one place at a time, right? And so a moment later, they're gonna be up here. So the key idea is that all the particles in adjacent loops on a stationary wave oscillate 180 degrees out of phase. And so the phase difference between 2 adjacent antinodes, right? All of these, sort of, here's the antinode, here's the antinode. Those are just like all of these particles. Every single particle right here is 180 degrees out of phase with every single particle right here. They all move down, they all move up. So the phase difference is 180 degrees. All right, let's take a look at giving ourselves some immediate feedback on this. And so this is paper 21 from October, November 2020. Let's see if I can't cue up the mark scheme here. Well, let's just say, yeah, they're all right. And we'll see you next time.